I think we might get started. That's right.
Yeah, sure.
Alright, welcome everybody to Marissa Bennett and Michael Miller in Absentia from University of Toronto, both from the University of Toronto.
Mm-hmm.
Yep. With the conventionality of real valued quantities. Thanks very much.
Thanks. Yeah, so in physics, obviously, or of course, it's commonplace to represent physical quantities, like classical quantities such as like mass and length, using the real numbers. Now, if you're a realist about physical quantities, then you might be tempted to draw certain inferences about the nature of these attributes from features of their numerical representation, right? So, you know, since our best theories are representing these quantities using the real numbers, and say you're interested in the metaphysics of quantity, you're interested in like the nature of mass or length itself, you might be tempted to draw certain inferences from the fact that our theories use those real valued representations. But first, like before, you know, drawing those conclusions, it's important to investigate what the existence of a certain kind of numerical representation actually implies about the attribute that it represents. So, how could we approach such an investigation? Well, we can draw from the resources of the representational theory of measurement, which characterizes the conditions under which an attribute admits of numerical representation. So this is a body of work, a collection of formal results, and the original developers of this theory, RTM, interpreted their formalism operationally. So they were the furthest thing from realists. However, there have recently been a number of efforts to reinterpret this formalism of RTM for the purpose of articulating a realist metaphysics of quantity. Now, realist accounts that apply RTM in this way tend to just inherit the assumption that the real numbers enjoy this privileged status in the representation of classical quantities. But this privileged status can be questioned. So, is the use of the real numbers forced upon us, or is this a conventional element of this representation? So, the significance of this question can kind of be summed up as follows. So, realist applications of RTM employ a certain pattern of inference concerning the nature of physical quantities. And the inference goes from the existence of a certain kind of numerical representation of the given quantity in the reals to the claim that the quantity itself has that full structure of the numerical representation. But if nothing forces us to use the real numbers to represent these, specific quantities, if the reals are conventionally chosen among alternative number systems for this purpose, then this pattern of inference would fail to be justified. So our claim is that there is an important sense in which the number system in which one represents quantities like mass and length does turn out to be conventional. And our aim in this paper is to give a precise statement of this claim, demonstrate its correctness using the framework of RTM, and to show that it presents a problem for the realist applications of RTM that we have in mind. So the plan for the talk is as follows. First, I'll present the basic elements of RTM along with its operationalist interpretation, as it was originally intended, and present the key representation theorem for quantities like mass and length. Then I'll explain how to reinterpret the formalism in terms of property spaces for the purpose of articulating a realist metaphysics of quantity. This is how the realist applications we have in mind proceed, and we're sympathetic to that general project. We just have some criticisms of the details. So following that, I'll present a series of results concerning representation in the rational numbers. These are novel results that we've proved using the same axiomatic framework as they use an RTM originally. And finally, I'll argue that these results demonstrate an important sense of conventionality in the choice of numerical structure for representing quantities like mass and length, and discuss the impact of this conclusion for recent efforts to apply RTM to the metaphysics of quantity. So first, RTM. So on the original interpretation of RTM, numerical representation consists of a mapping from, on the one side, an empirical relational structure to a numerical relational structure. So the empirical relational structure, or ERS, is taken to be a set of objects on this interpretation. It's a set of objects, each of which have the quantity in question as one of their attributes, together with a collection of operationally interpreted relations that are defined on that set. Now, the numerical relational structure is typically taken to be the real numbers, with the standard order structure and the standard notion of addition. So to make this more concrete, let's take a look at the example of length. So say we have a set of straight, rigid rods. All of them have some length, and we're interested in devising a numerical representation of them with respect to their length. So what we can do is do this comparison procedure. So this is going to establish a binary ordering relation on the set. So this is like an empirical procedure. You take two of the rods, you place them side by side, you line them up, and you observe which one extends past the other on the other end. And there's three possible outcomes, of course. So that's going to be the interpretation of this relation. And then there's, in addition to the comparison procedure, we have a concatenation procedure. So this is going to capture the additive aspect of length. So you can place them end to end. So you can, this circle just means concatenation. So we have A, B, and then this whole thing is the concatenation of A and B. You can think of it as a three-place relation or a binary operation, either way. But then concatenations can then just be treated like a single rod and enter into the comparison relation as well. Okay, so the observed outcomes of those procedures equip the set A of rods with these relations, and that's our empirical relational structure. So just like a little diagram. So here's an instance of the concatenation relation. Here's a couple instances of the comparison relation. And the empirical relational structure is going to be represented by a numerical relational structure. So the way this works, of course, is that addition in the reals is going to represent concatenation on the qualitative side. So you want to make sure that they are mapped in a way that preserves that structure. So we have these kind of parallel relations, and we want to make sure that we are mapping them so that we're representing the relations on the left-hand side and the relations on the right-hand side. So if our mapping meets that structure preserving requirement, it is a homomorphism, right? So this mapping being a homomorphism, these are the two conditions. This is what ensures that the structure is preserved in our mapping. And this, I think, underwrites like the utility of mathematics, why we can do arithmetic manipulations with numbers that represent them and be confident that we're going to be successful in our inferences with respect to the quantitative attribute of the objects that they're representing. So, with that in mind, the sense of numerical representability that's employed in RTM is given by this definition. So, an ERS is homomorphically representable in a numerical relational structure. So B is going to be some set of numbers, and typically these will just be the standard ordering and addition, if and only if there exists a homomorphism from A to B. So typically, almost always when you see this stuff in RTM literature, the set B is going to be the real numbers, or maybe the positive real numbers. But we are interested in exploring representation in alternative number systems, so we're leaving it general, just a general notion of homomorphic representability in some numerical structure. Okay, so that's homomorphic representability. Now, the precise nature of the empirical relational structure is articulated with axioms that specify the properties of the comparison and concatenation relations. So, this is the definition of a positive closed extensive structure, and this is the axiomatization for extensive quantities like mass and length, positive extensive quantities. So, in the interest of time, I won't go over each of these axioms. We can talk about them in the Q&A if you like, but I just want to show that how the relevant empirical relational structure is defined in just kind of the way this is set up. Just as an aside, positive quantities, this is called like the positivity axiom, and that is included in the definition of mass and length because there's no negative masses or negative lengths. So representation of these is restricted to the positive real numbers. Okay, so with those two definitions in place, we can then formulate a representation theorem. So this is the key representation theorem from the classic RTM text for these types of quantities like mass and length. So if we have just any empirical relational structure, then we have that the structure is a positive closed extensive structure, so satisfies that axiomatic definition, if and only if it is homomorphically representable in the positive real numbers together with their standard ordering and addition. So this is a theorem that they proved. The proof is pretty long, but it kind of establishes that the axioms for a positive closed extensive structure enable the numerical representation in a certain sense. Okay, so it's like good so far. So now it's important to recognize that the operationalist aims of the people who developed RTM, right? So they aimed specifically to give an operationalist account of numerical representation in physics, and one of their motivations was to legitimize numerical representation of attributes outside of physics, so like psychometrics and mathematical methods in psychology in general. So they took themselves to be showing that the use of mathematical methods in physics is enabled by operationalizing physical attributes empirically, just as mathematical methods in psychology is enabled that way. So they're kind of trying to put use of numerical representation in physics down like on a par with other sciences that people maybe didn't take to be, inherently mathematical. So all that they needed to do for their purposes was to account for the kinds of representations that are in fact used in physics, that exist in physics. Real valued representations are used, and they were explicit that the interpretation of the relations in the numerical relational structure, even in the case of physical quantities, they took them to be conventional. They didn't think they were unearthing some deep structure of the quantities involved or anything. So for them, alternative interpretations of those relations yield equally good numerical representations. So they had no reason to investigate whether the reals are uniquely suitable for representing the structure of these quantities. But for the realist, of course, if you're going to take these representations to be indicative or maybe like a perspicuous representation of the structure of the quantity itself, it is an important question whether the real numbers are privileged, uniquely well suited, the best numerical representation. So now we're going to talk about how realists reinterpret the domain, the qualitative side. So realists will take the domain of the mapping to be a property space. So you can think of this as the general quantity, like length, is like a determinable property, and then it has, as its determinants, specific lengths, like the specific lengths instantiated by objects. And then you think of the set A, instead of a set of material objects having the attribute, you think of A as the set of all possible determinant lengths, all the possible values that an object could instantiate for length or mass, etc. So then we interpret these relations as relations on that set of specific determinants of the quantity. And on this property space interpretation, it's just important to keep in mind that now we're talking about determinant lengths themselves rather than the objects. That's what makes up the set now. So there have been, over quite, for a long time, fairly long time, there have been people trying to come up with a formal theory for a realist theory of quantities. So, Brent Mundy in 1987 argues that we need to use second-order logic if we want to represent these values, because they're properties, and then we have to talk about relations between properties. But more recently, Joe Wolf, in a recent book, proposes a realist theory that maintains the first-order formulation, but requires the mapping to be an isomorphism. So if you remember, in the original formulation, it was just a homomorphism, just a structure preserving. But Wolf says that taking the mapping to be an isomorphism captures the realist commitment that the rich structure of the numerical representation is projected back to the physical world. So the idea is that the realist should look at these representations and take them to be isomorphic. Okay, so let's consider how certain aspects of the formalism relate to the two interpretations. So why doesn't the operationalist take the representation to be isomorphic? Well, just recalling that an isomorphism is a bijective homomorphism. If we have a homomorphism, it'll be an isomorphism if it's both injective and surjective. And the operationalist interpretation requires neither of those, right? So if these are objects, it's not going to be injective because our ordering relation isn't going to be anti-symmetric. You can have two distinct objects in your domain that are tied with respect to their order, and then they'll be mapped to the same number. So that's allowed. And then it doesn't have to be surjective because, who's to say that you have a set of objects such that there's going to be one corresponding to every positive real number. Like if your set has a least element, for example, there's going to be lots of gaps there. So it doesn't have to be injective or surjective, and that makes sense on their interpretation. Okay, but now when we move to the property space interpretation, why should we require both injectivity and surjectivity? Well, we think that it makes sense to think that it will be injective because we're not going to have ties between the determinants of a property the way we will with objects. That would just be redundant, right? Like, there's no reason for there to be two distinct determinant properties that are tied with respect to their ordering. So there's not going to be any elements that are mapped to the same number. But taking this to be an isomorphism requires it be surjective as well. And we don't see any reason why we should require this mapping to be surjective, or no reason to think that such representations used in theories are surjective. Okay, so this brings us back to our guiding question. Are we forced to represent in the reals, or could we get by just as well with, say, the rationals, right? So once you notice that the property space interpretation doesn't really require us to treat the mapping as surjective, while, you know, the rationals are a subset of the reals. So you could imagine a homomorphism to the reals that only maps elements to the rationals, and then you could just restrict the codomain. You have a homomorphism to the rationals, right? So now we'll turn to just the work we've done to prove some new results in the rationals. So this is kind of the key to how we are establishing this conventionality. So our questions are, you know, basically which axioms are sufficient for homomorphic representation in the rationals, and which axioms are necessary for homomorphic representation in the rationals. But we're mainly interested in looking at positive closed extensive structures, since we're talking about representing quantities like mass and length. So the first thing to notice is that not all positive closed extensive structures are homomorphically representable in the positive rationals. Yeah. So that's something you can come up with a counterexample for that. Now, next, we note that any empirical relational structure that is homomorphically representable in the rationals is just automatically homomorphically representable in the reals, right? Because the rationals are just a subset of the reals. All you do is just erase the codomain and put in the reals, and it will work. Okay, so those, you know, quite simple observations taken together with the results from RTM originally tell us that homomorphic representability of an empirical relational structure in the positive rationals implies that the structure is a positive closed extensive structure. So being a PCES is necessary for homomorphic representation. But since not all PCES are homomorphically representable in the rationals, it seems like, you know, some of them are, some of them aren't. So is there some axiom we can figure out to, like, delineate? So we figured out it's this, commensurability. So this basically says that for every two elements in the set, there's going to exist a third element that is a common measure of both of them, divides evenly into both of them. And that kind of makes sense, that that would be a feature of the structures that are homomorphically representable in the rationals. So this brings us to, this is like our main novel result that took a fair amount of work to prove. So given a positive closed extensive structure, then it is commensurable if and only if, so both directions, it is homomorphically representable in the positive rationals. Now, if you combine that with the original results from the classic text, this implies that being a commensurable positive closed extensive structure is both necessary and sufficient for being homomorphically representable in the positive rationals. Okay, so all that said, how does this bear on our question? Well, you might think these results suggest that the reals do enjoy a privileged status, since the axioms for quantities like mass and length are necessary and sufficient on their own for representation in the reals, but they're only necessary for representation in the rationals. You have to add commensurability to get the other direction, and that might seem like not a justified axiom to add. But this difference only manifests in the context of homomorphic representation, not isomorphic representation. So it becomes clear that the only advantage that the reals have over the rationals is that the reals are, like, big enough to accommodate homomorphic representation of PCES, whether or not they're commensurable. But if we turn to isomorphic representation, things look very different. So if we have a PCES, well, if it's isomorphically representable in the positive reals, then it's incommensurable. There's the negation, commensurable. So if we require that representation of this type of structure in the positive reals if we just require it to be an isomorphic representation, that's just stipulating that the represented structure is incommensurable. Similarly, with, say we started with a rational valued representation, we just stipulate that that's isomorphic. Same thing, we're just stipulating that it's commensurable now. So basically, the upshot here is that when we require that representation in a specific numerical relational structure is isomorphic, that's just to stipulate that the empirical relational structure shares certain structural features of the numerical structure that are not implied by the associated homomorphic representation. And being homomorphic is like the key thing that explains the usefulness of the representation. That's all you need to preserve the structure. Okay, so, do you know how much time I have left?
Yeah, you've got like 4 minutes because we started a bit late.
Okay, perfect. Okay, so just we'll wrap up by just driving home some of our conclusions. So again, we think we've answered this question. So there exist positive closed extensive structures. So the structure that we think these quantities, mass and length, have. This is the axioms for that kind of structure. So there exist, okay. So we have an axiomatic definition. There's different models that will fit this definition, right? So some of them will be incommensurable, some of them will be commensurable. So there do exist some positive closed extensive structures, which are homomorphically representable, just as well in the rationals as they are in the reals. So absent any additional argumentation, there isn't an obvious reason to believe that quantities like mass and length are not among those that are homomorphically representable in the rationals. So if we just default to a representation, reals, rationals, maybe something else, based on one or the other of the number systems, that's a conventional choice. So we think that's been established. So then, if we naively demand that our conventional homomorphic representation in the reals can be strengthened to an isomorphic representation, then we're indirectly demanding that the PCES exhibits incommensurability. And it's not clear that we have any reason to think that it does. And then if instead we start from the homomorphic representation in the rationals and demand isomorphism, we indirectly demand that the PCES exhibits commensurability. And the problem with this, of course, is that conventional representational choices aren't the sort of thing that can tell us anything at all about the nature of the structure being represented. So, to have a little bit more time, so you might be wondering, what does it mean to what is it that we're even unsure about when we're unsure about which type of structure these classical quantities is. So this is just my attempt to kind of just translate certain features of the real numbers into the language of the property space. So incommensurability. So that would mean that, say we're talking about mass, that would mean there's pairs of values of mass, so there are specific masses that objects could instantiate for which there does not exist any possible mass that would divide evenly into both of them. It's a pretty strong claim. Uncountability, of course. We're saying that mass, for example, has innumerably many values, right? I don't know what reason we have to think that. And then completeness is a little bit more tricky, but basically, right, so there's infinite sequences of values of mass, such that you can take the sum of all infinitely many elements, you'll get a finite, a bounded mass value as a result, and all of those sums are again going to be members of the set of masses. Same for length. I'll end there. Thank you.
and the paper. I think both were very clear. And towards the end, we will come back to that because you mentioned in that last slide some things that partially suggested some of these comments. So first, well, it's going to be a combination of reading and talking. The paper shows that requiring isomorphism between an empirical relational structure, say the structure associated with mass, for example, and the structure of the reals with addition and an ordinary relation implies that the empirical structure is not commensurable. That's the thing that you proved, Mike, towards the end in the presentation. Similar, they show that requiring isomorphism between the empirical structure and the structure of the rationals implies that the empirical structure is commensurable. From this, the authors conclude that the conventionality element regarding the choice of numerical structure, reals or rationals, can lead to unjustified inferences about the empirical structure itself, right? You use the rationals together with isomorphism, you seem to be committed to, or it follows from that you are taking the empirical structure to be incommensurable. And the other way around, if you use the rationals instead of the reals, you say the structure is commensurable. Okay, first a minor point, although I think it's more clear, it is clear in the slides, I think now, which is there are different levels of conventionality involved, right? The first one, or I think the one that I thought was more prominent in the paper, was this thing between rationals or reals, right? Which system we use, the rationals or the reals? Is this like a conventional choice? Another thing that is conventional going on here is the choice of the connection between the structure, the empirical structure, and the numerical system. So you can use reals and isomorphism, or you can use reals and homomorphism, right? So there is conventionality at that level too. The connection between the empirical structure and the empirical structure and the numerical system, and the conventionality about which representation, relation, or whatever this mapping, how does this mapping work between the two. So more than, I guess, a question is maybe commenting that there are different conventionalities that could be going on parallel to each other. So maybe you can say something more about this, whether you think these are other conventional choices or is part of the same conventional choice you were referring to. Second, and more substantively, it would be useful if the authors elaborate on why the literature, and I guess the literature in this case really focuses on this book by Wolf, right? That Wolf, according to, well, I didn't read the book, but I read your paper, says that you need isomorphism. If you are a realist, it would make sense to demand isomorphism. But you are showing that that's too much, because if you demand isomorphism and then you choose the reals, you seem to be committed to certain things about the empirical structure that you don't have reasons to be committed to, like being incommensurable, for example. But now I'm wondering, like, why if there is more you could say about Wolf's justification for using, for example, isomorphism, and then see what is lost if, for example, we were to accept your, there is a way of taking your paper which is, don't use isomorphism, it's just too strong and we don't have enough arguments right now to rule one or the other one. So maybe go back to the homeomorphism. That's a way by which one can read your paper. I wonder if there is any specific things about realism that Wolf thinks really require commitment to isomorphism as opposed to homeomorphism. And one thing I mean, just thinking kind of aloud, is the literature on scientific models and representations, right? Scientific representation has for a long time now thought that isomorphism is too strong too, right? Demanding that, I don't know, the hydrogen molecules you use in the model are isomorphic to the actual structure. I mean, there is all these approximations and idealizations involved in science. So I just don't know if Wolf interacts with the literature, why Wolf is going to isomorphism. On the other hand, homomorphism might be too weak, right? Many structures that in a way look very different can be mapped homeomorphically, is that how you say? Okay. And maybe that's too weak, and so maybe the realist requires an in-between position between those two things. I don't know, I would like to hear your opinion about why, what's lost if you go to the isomorphism. And then the other question that I shared with you at some point was about so what kind of techniques or theory, or by what means can we ever come to figure out what's the structure, the empirical structure like, right? Like, is there a way, you think, by which we could use either theory combined with maybe experiments, a combination of those two things, by which we could figure out that the structure of the property space is commensurable as opposed to incommensurable? Or maybe not. Maybe this is like maybe more like a skeptical worry and we will never be able to know. And if we can know, I'm just curious to see how, because physics use the reals in a lot of times, right? And there is all these conventional choices going on also in the physics side of things. So it looks like a very hard project, and then maybe what you show is maybe some skepticism, or at least just pausing and not commit to one. Like, just we'll never know basically if it's commensurable or not. The space of mass. I don't know. Yeah, and then finally, you can choose any. You don't have to touch on all of this. You can choose whichever you want. The last comment had to do with the realism side of things. You, I think, kind of think that you can still be a realist. Like your project is compatible with realism, right? And then I guess I would like to hear more about what kind of realism we would arrive to if we go through your route, namely a route where isomorphism is too much and we don't have reason just to choose it. Like, so what is kind of the realist picture that emerges here, like some sort of structuralism of some sort? I don't know, but yeah, those are my comments. Thank you.
Brief response.
Yeah, okay, so those are excellent questions, very on target. So first, the suggestion that the choice between treating the mapping as a isomorphism versus a homomorphism might be similarly conventional, just like the choice between using the reals and the rationals for representation. So I think we take the choice of numerical number system to be a convention that exists like in science with long established history. So we're pointing out that this element of that scientific practice is conventional. Now, I don't think that physical theories, like in science, I don't think they'll specify whether they take, say you have like some laws that you have like functions relating different quantities, a function of time. They'll just say like, the value for this mass variable is an element of the real numbers or something like that. So I think talking about whether, talking about a property space of quantities in the first place, or thinking about it in terms of operationally, in terms of objects, more instrumentally, those are, the question of the nature of the mapping is like a philosophical interpretation, I think. So, yeah, and then the participants give their arguments for and against. So we don't think choosing homomorphism as the better way to interpret the mapping is conventional. Yeah. So the next thing was, what do we, what are we losing when we aren't willing to regard it as an isomorphism? So this is related to the question of what the commitments of a realist about quantities in particularly are supposed to be. Strangely, like quantities in particular have been like neglected for a long period in the history of philosophy of science. So this discussion is fairly new, like what it means to be like a realist about quantities in particular. So quantities just kind of, at first, are thought of as just, those properties that we represent numerically, that seem to be, perspicuously represented with numbers. So when you're a realist about quantities, or maybe like a specific set of physical quantities, there's a question of, okay, so yes, you take these to be, real properties, but there's supposed to be something distinctive about quantities. They're supposed to be structured in some way. There's something about them that makes them suited for numerical representation. So I get that there's a need to kind of fill in the content there. Like, what are you a realist about? Yeah, does that make sense? Right, okay, so the question exactly was, yeah, what is the cost? So yeah, so if you deny isomorphism, then, I think the main, it's a bummer because you don't really know the structure that you're a realist about, that you're supposed to be a realist about. It's at least epistemically, epistemically indeterminate in some way what the structure is that you're supposed to be a realist about. So I'm unsettled somewhat. Okay, so next. Yeah, so I am very pessimistic about the prospects of empirically confirming whether mass, length, temporal duration are either commensurable or incommensurable. There are some arguments out there, like Newton-Smith, in the context of time, temporal duration, that are pretty compelling, that this is like, in principle, we could never know. So our position is just that if we could be justified in the claim, it would have to be empirically justified, because it is a substantive claim, and it just, we don't think that just, taking the numerical representation that can be explained with the homomorphism and then just saying, well, let's just say it's an isomorphism so that we can, act like we know what the exact structure is. So not justified, but no groundbreaking ideas for settling the question. But that relates to your final point, which is, a very good question. What metaphysical picture of quantities emerges if we do just restrict ourselves to treating these mappings as homomorphisms? So yeah, in the talk and in the paper, most of the points were negative. Now, I don't know how far along Mike would go with me on what I'm about to say, but I'm interested in the idea that you'd have a structure. So I think that the axioms for a positive closed extensive structure are the whole story of the structural features of these quantities. Now, doesn't really make a lot of sense if you think in terms of model theory, right? There's going to be determinate structures that either do or do not satisfy commensurability and myriad other axioms that you could think of adding to that. So the idea that I'm kind of developing, and I'm thinking about this as part of my dissertation, is that this is a structure that is in some sense metaphysically indeterminate. So now you don't have to conclude anything like that, I don't think, from taking. You could kind of treat it as just kind of epistemic humility, because after all, a homomorphism could be an isomorphism. It doesn't have to not be. So when you just regard the type of representation that's being used in theories of these quantities as a homomorphism, you're just kind of remaining neutral on whether the quantity, or however you're interpreting the representation, what's being represented in the first place. So you could think of it as just kind of like epistemic neutrality, or humility of some sense, or you could kind of make that into a metaphysical view by developing some sense in which there's no fact of the matter about whether it's commensurable or incommensurable. Thanks.
Got a little bit of time for questions, so start with Z.
This is a little one. I'm just wondering what sort of things you would think would count as empirical evidence for incommensurability. So, for example, imagine we had a really good theory that just said that like, when there's when a particle has a particular property, then there is this then everything that is within distance p of that particle, inclusive, all those points exhibit some field, but everything outside doesn't. Like there's a sharp edge to the field. And then it seems like if you're a subcatalist about space, you're going to say, well, look, there's a class of points that are just the ones that are the furthest away from P that have this field up. They form a curve. Their length is incommensurable to P.
Oh, I see. Yeah, so so there's, people will argue that we do have good reason to think that, for example, length is commensurable because all I have to do is take a square of side length 1, and why shouldn't I be able to draw a square of side length 1, and then I can draw this line, and this is going to be root 2, and these two are going to be incommensurable. So some people might think, look, I just demonstrated that length is incommensurable, or Euclid, or not Euclid, the Pythagoreans did. But this is a mathematic. To my mind, this is a fact about mathematics, mathematical world, ideal. Perfect squares don't exist, arguably, and physically instantiated. So we're just talking about physical lengths, and really the question is, how well does our geometrical understanding of length, idealized length, line up with worldly length, right? So I think Poincaré has an argument along these lines, and Newton Smith said something like, it had to do with the fact that certain curves should have to intersect each other. And Newton Smith responded by saying, well, if length were discrete, for example, we could just change the definition of intersection in an appropriate way. I can't remember the details, but there are historical precedents of these kinds of discussions and interesting responses on both sides.
Sure. So it would have to be the laws would have to somehow make use of those relationships in a way that's ineliminable for you to think that would be good evidence for it. Or do you think even in that case we should actually think there's the potential for some other weirder theory that still gets around it?
Yeah, so that's another strategy. So Newton Smith, in his book, The Structure of Time, from 1980, I believe, Newton Smith just very recently passed away, actually. He argues that, so he sketches how you might develop a rival theory to Newtonian mechanics that only uses rational numbers. He called it not-Willis mechanics. And he argued that they're empirically equivalent in a very strong sense. So that is an example of how somebody might argue for conventionality again. Now, how might somebody argue for the other side? I don't know, because it would you would just have to say all attempts to make a theory that's as good as one formulated with the real numbers will fail, so you'd have to wait forever, I guess, for that. But yeah, I can't think so yeah, I don't think this is something that can really be empirically settled. Yeah. Sorry, I hope that language addressed things.
Seven.
Thanks, really interesting. I was wondering why one couldn't apply or invoke some kind of Occam's razor idea to say, well, if you're telling me that I can go for either rationals or reals, well, I should go for the rationals. I shouldn't assume that more things exist than are required to explain everything. So, and I want to be a realist, so I'm going to take the commensability with me based on that.
Yeah, you could go that way. As far as parsimony arguments go, that seems like it would fit for sure. But there's also so I think parsimony, fewer ontological commitments. I guess the kind of rival consideration would be how much more difficult calculations get when you're restricted to the rational numbers. So you lose continuity, differentiability, all the apparatus of calculus, which is obviously a big deal for a theory. So, somebody might come back and say, well, so those are mathematical techniques that rely on real numbers. This is like inferential utility. There's no reason to take all those, irrational numbers that are filling in the blanks to be, genuinely representing the values. You could take them to be, this sort of thing I think is pretty common in science, where you go outside, you take a detour outside of the math that you take to be kind of representing the situation, like bringing in the complex numbers to solve equations, stuff like that. Yeah. So I'm reluctant to get on board with the parsimony arguments, because I feel like it's a similar spirit. Somebody could come back and be like, the simplicity of actually checking your predictions is going to be so much easier if you use the real numbers.
Actually, two questions. One is more clarification also. I'm wondering, what's the set of measurement that we're thinking? We've been thinking about length, but are we thinking about all the measurements? Because I feel like it's context dependent. I can measure the number of particles, which can only be
so it's not every
natural numbers, right? So what kind of physical quantities we're talking?
Yeah, that's a good question. So I kept saying quantities like mass and length and temporal duration. So those are the three quantities that are explicitly mentioned in the Foundations of Measurement text, where most of these results come from. So these are like classical quantities. They're continuous, so not discrete, like counting particles. They're extensive, meaning there's a meaningful notion of addition. So it makes sense to talk about, so if I have, silly example, but if I have, a water bottle, okay, if I have my iPad and I have my laptop, and I want to know how much it's going to weigh to put them on my backpack, it makes sense for me to add the weights of those two and come up with this total weight of electronics. But not all quantities, same with length, right? It makes sense to add them in full interpretation. But temperature isn't like that, right? It's on the, at least on the Fahrenheit and Celsius scales, right? It's 50 degrees today, and it was 25 degrees the previous day. It doesn't make sense to say it's twice as hot today as it was yesterday. So, yeah, part of the whole, part of measurement theory, beyond just the representation theory of measurement, is a pretty technical field that involves classifying all the different types of quantities according to their scale type. So these quantities are kind of at the upper end of the strength. They're ratio scales. They have meaningful ratios as well. So yeah. Yes, right.
Do we have time for you? So it's more like a follow-up. So you were saying, for example, for length, choosing real number representation or the rational number is empirically equivalent, but it has quite a strong metaphysical implication of how the real world is, right? It's not, if it's rational representation, then it's not continuous. The space-time is not space is not continuous?
That's another really interesting question. So continuous is itself not really a technically precise term in mathematics, unless you're talking about a continuous function. So there, you can distinguish between a property that the rationals do have, density. So they are kind of continuous in a sense that between any two rationals, there's another rational. Continuity is, I think, kind of like an intuitive notion that, when is associated with like geometrical lines and what we previously took matter to be like infinitely divisible before particle physics and all of that. So the rationals are dense. That's kind of a notion of continuity. The development of what's the term for the real numbers that's stronger than density? I can't remember. It's a basic term that I'm just blanking on. But
isn't that the subject of the continuum hypothesis?
Well, that's related. Not what I'm thinking about, but yeah. So anyway, it's much stronger, right? Like it's filling in all the gaps. There's a lot of different ways to characterize it. You can talk about like Cauchy completeness. You can
the codes are you talking about?
You can construct the reals that have this strong notion of continuity from the rationals using Dedekind cuts.
Yeah.
Sequences, lots of ways, but yeah, it all is kind of motivated by this idea that we have things like the diagonal of the unit square, and where that can't be a rational number, so there's like these gaps. If you are kind of committed to the existence of even just abstract geometrical lines and that these have lengths, then if you're restricted to the rationals, you're missing the tools to express those lengths. Now, that is a really cool result of the minds of certain human beings to come up with this notion, and it's also extremely applicable and really, really useful. But there's tons of examples in mathematics of different, just within pure mathematics, different branches of mathematics being applicable to other branches of mathematics. And these ones are approximating those ones. This one is being used to study that one. So absent some more direct empirical evidence, I guess, than just the fact that expanding your representation to include all the real numbers makes us make more expedient calculations and predictions. I don't see any reason to think one way or the other that temporal duration, physical length, mass is strongly continuous in that sense. And in fact, Mike has an interesting paper where he argues that if you zoom in on uses the example of his height, you zoom in far enough, you're going to get to the quantum level. Then you're going to get to a point where even if you grant that you could specify the top molecule that's the top part of its head, you're going to get to a point where it's indeterminate the location of that top quantum system or particle or whatever. So at a certain point, there's if you try to go to an infinite decimal expansion of this height, there's a certain point when metaphysically there's just no fact of the matter beyond which what the rest of the digits are when we're asking about his height, because it's just actually, if you accept that interpretation of quantum mechanics, that they have indeterminate positions in certain situations. That's called fundamental yet imprecise. That paper.
Okay, we're out of time, so let's thank Marissa.